at least we can start. So we actually discussed what our computer has, and then there are different types of computers. So this is a very high level computer classes, but nowadays, in fact, there are many different types of computers. So then, what we want to show you here is that depending on the computers, we need to design the computers in different ways. Why? Because what's emphasized are different. So, for example, the home computer kept on a desktop and used by family members for emails, web browsing, social networking, and move.
Hi, do you need help with the system?
Yeah, actually, this one is not working. Somehow, I transferred a few files to this desktop, and then I'm actually using that.
So you okay for now, or do you want us to fix it, or you?
Yeah, this one has to be fixed.
Okay.
Later, but if you can fix soon, then maybe.
Let's see.
So they actually cannot recognize. You can see the laptop. We always show the screen in this laptop.
So you're trying to hook up this, right?
Yeah.
HDMI.
You want the drill?
So here, it looks
That's
like.
switching it off. Yeah, we're gonna need the drill.
Is there a deadline on the front of the switch?
Yeah, it's always like this.
No. We just gotta open up the back. We'll be quiet if you wanna keep going. I mean, it'll take like 2 minutes.
Okay, sure. What is
Oh yeah, you can turn that off.
So maybe we can continue. So here, home. So this one, the home computer comes on the desktop and used by family members for emails, web browsing. So we are actually using this kind of computers daily, right?
If we do this, everything's gonna shut off for 5 minutes. Do you want us to come back? And see? Huh? Come back?
Yeah.
He's gonna lose it.
It's all gonna go off.
Okay. I'm sorry, some language here. So this one is what we among these four classes, this is what personal computers, right? We call PC. And then also a computer in an Amazon building accessed by thousands of people for online shopping. This is what a server is used, right? So what server computers are used. The next is a computer in kind of pacemaker, which delivers an electric shock to keep a human's heart beating properly. This one is what is the embedded computers, right? Or this can be server or it can be a supercomputer. Let me see. So server, yeah, server. But so supercomputers nowadays not only used for server, but it also used for scientific workload. So I think that's how these authors actually classify computer types. So we have different types of computers, and then so this is what computer abstraction is. So starting from physics, devices. So this one, we talk about transistor level, and then while using these transistors, we actually make logics, so analog circuit. So these are actually the same thing you can think. So analog circuits and digital circuits we both use. And then using this, we make some logics. So adder, memories we make. So adders are combinational logics we call, and memories are we call the sequential logics. So both are actually logics. And then using these logics, we make microarchitecture. And then using this microarchitecture, actually what we do is this. Every time we move to the next level, we actually abstract everything away, right? So when we work on the microarchitecture level, we actually don't need to know the details of logics. Why? Because we just abstract everything away. So we just know how they work. But we don't need to care about the details. So again, when we work on the architecture, we do not actually need to know the microarchitecture. So I mentioned this, right? Like I'm working in this level, and then but we don't much care about how hardwares are actually implemented. When we also work, this is what software level, right? So when we work on the operating system, also we don't need to much care about how the architectures are implemented. Why do we study? At least in school, I think you guys have to know the basics of this architecture. That's why we are studying this. But the details, in fact, depending on your job. By the way. So if you work on the application level, then you actually don't need much. You actually don't need to know much about this architecture level. But if you are working in operating system level, then in fact how the architecture is implemented is sometimes quite important. So why? Because even though we try to abstract everything away, but when we optimize the software, we often need to know the details. So in this in this course, what we focus is this four, particularly this architecture level, and then these three also we briefly study. So yesterday I mentioned, right? So how did we get this big computer improvement? Is because of the transistor size is scaled quite good, right? So the number of I will say it this way. So the number of transistors are actually quite scaled well. Why? Because we were able to get smaller and smaller transistors every year. So this one started from 1970s. So the processor has just 2,000 transistors. So this is Intel. So it's probably hard to see. It's Intel 4004 processor. And then at that time we only have up to 1,000 transistors inside. However, the time comes, and then here, you can see we have how many? This is 1 billion, right? 50 billion. Around 30. Here is around 30 billion, right? 30 billion transistors in a processor. We actually, I mentioned yesterday, right? So last class. So we still get more and more transistors. So not this. This is by the log graph, right? So not this speed. So this is you can think that it's exponentially increased, but not this speed. But still, what? It's a little bit slowed down, but still we get more and more transistors. So the number of transistors are quite important for us, and the size of the transistors are also important. So we will study why here. Oh, again, another thing is technology scale. So this is the size of the transistor, right? Particularly, what size is this? Do you know? Yes?
Nanometers?
No, nanometer, that's true. This is nanometers, but the size of what? It's not exactly the size of the transistor, by the way. The size of the channels. So what is channel? I will explain in the next slide. But so this is, in fact, we don't know what the actual size of the transistors, but what's the matter is the length of the channels. So, and then also the length of the channels are 90 nanometer, and then so you can see every 2 years we make this length quite smaller and smaller, and then so from the certain point, I think from around this point, in fact this length does not exactly mean the channel length. Why? Because we already reached the almost the physical limitation, so we cannot make the channel length smaller. However, we still make something smaller, and then what? So what is something we don't know? The different vendors use different the component. Different vendors measures different component. So we don't know what's exactly 7 nanometer. So nowadays, you can just assume that this is a version number, the transistor version, 7 nanometer transistor. We exactly do not know what's the 7 nanometer in the transistor, but this is after 10 nanometer. You can just think in that way, because now it becomes like a marketing term. But originally, and also in science, we actually used this term for the channel length, transistor's channel length. So this one, I will just so this is the steps how we implement chips. So we start from the silicon ingot, and then what we slice, and this is wafer. And this in this the silicon wafer, we actually implement our chips. So what here in this wafer, you can see that this rectangle is a single rectangle is separate chips. And then what we actually test, and some are failed. And so what some are survived, so then what using these survived ones, we do packaging, and then what we do the testing again. So then what is shipped to the customer. So then here what's the important is this one, how many survive and how many fails. That determines yield. Right? And then so what this yield rate is actually changes everything. So for example, let me see. This is an example of the Intel Core i7 wafer. So what this small rectangle is one chip, those chips. But not all can become a chip. So there are some failed ones. So how many survive is determined by yield rate. So here, I just briefly introduced what's going on in industry. So here, this is U.S. companies. By the way, the chip manufacturing, U.S. actually dominates the market. You can think in that way. So this is a little old, dated. So it's 2019. So still Intel is rather big, but now it's quite different. See, now where's NVIDIA? NVIDIA is small at that time. But now NVIDIA is huge and something like that. But so anyhow, this is 2019. The still U.S. Dominates the market, so you can see the size of the market here. Europe actually has a few companies, so Infineon, STMicro, and ASM. ASML is also one key company, right? They are making manufacturing tools. So what they make, they actually they are the only company which make the EUV technology, right? So that's the most recent technology. So EUV technology is the ASMS the patent. So then what if any companies want to make the process with the best chips, then what they have to use ASMS tools. Then the interesting thing is this. Okay, then what? Most companies. So okay, before we go there, what's the color means? We can see too. So this is what color? This is cyan color maybe. So this color is what indicates chip design software. So there is a synopsis and cadence. So not many companies actually working in this chip design software. So but Synopsys is one of the most famous company, and I saw many actually use these Synopsys tools. And then also there is a cadence. So and then the yellow ones is the equipment company. So they are actually making the manufacturing tools. So they are the most important key company is ASML, but also there's Applied Materials and Lam Research and KLA. These companies also are making the semiconductor manufacturing tools. So okay, these are some secondary companies we will consider. And then what's important is these three, right? So first one is fabless. So you can see most companies here, there is NVIDIA, AMD, Broadcom, Qualcomm, Texas Instruments, all these, I believe that you guys heard all these companies' name. So these companies we call fabless. So what they actually do not have factories. What they do, they just design chips. Right? So this is fabless companies. In fact, Broadcom, they have a factory, but probably the size of the factory is not very large, I believe. Texas Instruments, they have also factories, but the factory name we call foundries. So they have foundries, but their foundries produce processors with old transistors. So their factories do not do very well, as I know. So you can consider all these companies as family companies. Micron actually has a foundry, but they are DRAM companies. And then so the one major foundry company in US is Intel. So Intel actually then foundry companies are this purple color, right? And then what's green then? So foundry companies, what they do is that they only have factories. So what they do is this. So these families companies make designs, and then they ask these companies, foundry companies, to produce our chips. So then these foundry companies manufacture the chips. Then what's the green one? The green one is they have both, right? So they design the chips, and then they manufacture the chips. So Intel is one of the major companies, the IBM company. So they both design and manufacturing the chips. So you can see US actually had dominated the market, but most of US companies do some software work or just do some designing the chips. Intel has factories, but nowadays their size actually shrink quite a lot. And then it has Micron, but the Micron is a DRAM company. DRAM actually does not need high-end technology, by the way. So this is what's going on. And then Europe does a small part of the work, but their size is becoming shrinking too. So the only major company is ASML, and the other companies are becoming less and less important nowadays. So and then Asia actually. So there is Samsung, TSMC. So this is also some native revenue. The TSMC's revenue is much larger than Samsung nowadays, I believe. Hynix revenue is even larger than Samsung, and almost a similar size maybe. And then some SMIC, they actually this Chinese company also produce many chips nowadays because of the current political tension. So okay, but what I want to emphasize is that so mostly manufacturing is done in Asia, and then also designs are done in US. That's what's still what's happening. And then this is some also history. So here this is 90 nanometer chips, transistors. So when we produce chips with the 90 nanometer transistors, these many companies were able to produce chips. However, you can see the trend. So here is a 16.5 nanometers. So then what less companies can produce chips, and then less companies, and then what this is a 20 nanometer chip, right? So then what only 4 companies, Global Foundries, Intel, Samsung, and TSMC can produce chips. Global Foundries are just in the urban, by the way. So, and then the 10 nanometer. Again, Global Foundries, Intel, Samsung, TSMC. Currently, we are producing chips in the 3 nanometer, with the 3 nanometer transistors, right? So then what? Currently, the only TSMC actually produces chips with the 3 nanometer transistors, and then the Samsung is following TSMC, but I heard that their transistor quality, their transistor size is larger than TSMC. Intel is actually quite behind. We are not actually sure that Intel actually produces chips with the 7 nanometer transistors even. So they are actually quite behind. So then we may have questions here. So I just mentioned that, right? Like the technology, the transistor manufacturing technology is ASML's technology. So as long as we purchase, any company purchases their tools, then what? Of course, their tools are very expensive. But as long as the company has the money, and then what? Purchase their tools, then what? They can produce chips with the best the transistor technology, right? But then why this happens? Why only 3 companies can produce? I mean, it's not their technology, right? I just said it's ASML's technology currently. But then why only 3? In fact, not even 3, right? 1 or 2 companies can do at this level. TSMC currently trying the 1 nanometer transistors. But why this happens? Their technologies are all same, yes?
Expertise or like just equipment they have available?
But the expertise, that's actually the good answer. So, but then what can be different, you think?
Like kind of like the personnel, the people know.
Yeah, so that's true. So in fact, so then what changes this? In fact, everyone uses the same technology. However, what changes here? Yeah, so those companies can have better yield rate, and then that's basically because of the experience. So then what? So interestingly, in this business, every time they have more and more experience, then what? They have a higher chance to produce chips with better yield rate. So that's why one company becomes market dominators. So why? Because once they make chips with the best transistor technology, then what? All companies actually orders their chips to that company. Then what? They actually have more chance to experience. Then what? They can have better yield rate. So then what? They can try even smaller transistors, and then also what? Since they have more experience, so what? They also have a higher chance to. They actually have a higher chance to produce chips with better yield rate. So this yield rate determines everything. So what currently I just said that Intel doesn't do well, and the reason is because Intel actually adopted the EUV technology quite late. So when around middle of 2010s. TSMC and Samsung actually employed their ASML EUV technology. So this UV technology is not just a simple the tool. In fact, their tools are almost a factory size, the building size. So what they do is that they first build the tool first, and then on top of that they build buildings there, something like that. So in fact that's quite expensive, and also it takes time. So why in the middle of 2010, Samsung and TSMC adopt UV technology, and then what Intel did at that time is that the CEO at the time, so around 2015, something like that. So the CEO of Intel made a wrong decision. So what he did is that we had best engineers in the world, and then that time they were using the DUV technology, and then they tried to improve DUV technology instead of adopting the EUV technologies. And then the CEO actually believed that using DUV technology, they were able to produce better transistors. They believed, and then they failed. So that's why so around 5 years later, I think around 2020, Intel CEO was fired. Then next CEO came, and then he actually admitted that they did a mistake, and so they adopted the technology, but it was already late. But then the experience is important here, because that experience actually determines the yield rate. So that's what's going on here in current industry. So this is 2021. And then fabrication capacity. So most fabrication is done by Taiwan. This is what TSMC does. And then the Samsung and Hynix does this many. And then Europe and the other countries do 2%. So this is what's going on. This one is all logic capacity. So this one is including old technology, so DUV or kind of older technologies. Then China also actually produce high numbers of chips. So, but the high-end chips are only made by these two companies, you can say. So that's the current market trend. So, do you have any question? Interesting or? So before unfortunately when Intel was this large, there was many so around 10 years ago, right? So many students wanted to study computer architecture because Intel actually hired a lot of people at that time. But nowadays they are shrinking, so they are not hiring people as many as before. That's unfortunate. But I think they will be better in the future. So, that's just my belief, my hope. And you guys want to try to study computer architecture more, I believe. So then, before I move to the actual computer architecture, we may need to study these transistors a little bit. So, and then you don't need to know the very deep inside. So if you study in ECE, then you will study this very deep, and so. But you don't need to just you can just understand the basics, and it's okay. So we use semiconductors, right? So then using this semiconductor, we try to control electrics. Right? So the electrics are very similar to water, you can think. So then controlling this water is not easy for human being, right? So what we usually do, we make the path for the water, and then sometimes we build a dam, right? And also sometimes we try to change the position of the water, right? So maybe we place the water higher position than so that we can use the water in the different way. So that's what we do. So what here, when we deal with the electrics, we also do the same thing. However, again, like water, it's not easy to control. In fact, electrics are even much harder than water, but almost similar concepts. So then, what the most important thing is this, right? Like we have to make where the electricity flows, right? And then what also we should be able to control this. Sometimes we can flow, we can make the electricity flow, or sometimes we should be able to stop they are flowing, right? So such kind of control we need. How can we do? Using semiconductor. Basically, we try to do that is using the transistors. So then, when we make this transistor, what we use is this silicon, right? So this is from sand. And so then this is a silicon lattice. So this one is insulator, right? It's a very poor conductor. It actually, the electricity cannot flow using this silicon, right? So something like silicon is what it is. So glass, for example, the glass is silicon, and then what? Electricity cannot flow here, right? So that's what silicon lattice is. However, if we add some small impurities, then what? We can make this the silicon to conductor. So then what kind of impurities do we need? So sometimes this is what? This one is AS is, just forgot. AS is, B is a bottom, but AS is Arsenal is soccer team. AS, let me think. What's the AS? AS. AS is 33rd one. AS is arsenic. Yeah, arsenic. Sorry. So this is arsenic, but the name is what's the important is what? So when we add this arsenic here, then what? What we get is this free electron. So what this is they are actually bonded tightly. But what after that we get the extra electron here. And then also what when we add a bond here, then what we get a free hole here. And then what using this free electron and free hole, we actually make this the semiconductor. I mean this silicon to a conductor. So then what's happening is this. So when we attach this n-type, so we call this is n-type and this is we call p-type. So when we attach this n-type and p-type, then what happens? Somehow only current flows from one direction. So what in fact current flows since there is a free electron. So what current actually flows from n to p type, but you can think that p type has the higher voltage than what electricity start to flow. But the p-type has a lower voltage than what in fact the electricity cannot flow. So using this, we can make electricity flows to one direction. We now can control electricity somehow, make it flow only one direction. That's the first we can do. And then so we call that as a diode. So p-type and n-types are attached. Then what we draw diode in this way, right? You probably, I believe you probably know. So what here, there is a p-type, and then here n-type, and then what? The symbol is we draw in this way, right? So something like this, right? This is a diode indicating what current flows one direction. Current flows one direction. So we draw diode in this way. This is diode. And then what? In fact, as a resistor, we add one more type here, right? So the NPN or PNP. That's what transistor does. It look like. So then what? This is how the transistor look like. Using what do we do using this transistor? We implement a switch. So then what? How this transistor look like is this. So here there is n-type, and there is a p-type. And then this one is a metal. So this is a polysilicon. You can just think this is a metal. And then this one is SiO2. So this SiO2 is what? You can just think I think SiO2 is this is sand, almost sand. This one you can just think insulator. So then what? There is a metal and there is an insulator, and then what? P-type is I just said is a conductor, right? Conductor and conductor there, and then in between there is insulator. What is this? Look like this one. Look like capacitor. Do you know the capacitor? How it looks like? So what? There is a conductor here, and then another conductor here, and then what? Sometimes there are something here, or sometimes it's just air. But anyhow, you can consider this is the insulator, right? So then what? This one behaves like a conductor. What conductor does? It keeps energy, right? Energy in between. When we build a battery, so we use these conductors. So this is, and then what? In fact, this transistor has this conductor capacitor here. So how it operates? We just briefly see. So here, this is, by the way, MOS. So what here, N-type, this is another N-type here, and then this is a P-type, and then there is a ground here, and then there is, this is what? Insulator. So this is the insulator, and this is a metal here, and then what? This is also a source gate, drain here, and then what? I just said that electricity can only flow from N to P. Let me see. No, not exactly. When P has higher voltage, then what can flow? But here, the P has a low voltage here because it's ground. So then what? Actually, electricity cannot flow. Why? Because source has some like voltage. You can think maybe 1 volt here. Here, this is 0 volt. Then what? Electricity cannot flow. Why? Because P-type has a higher, lower voltage. So what if this one has a higher voltage, then the electricity can flow. But what? This one is fixed. You can think. So then what? Electricity cannot flow. So then what? We actually stopped electricity. So what? We want to make the electricity flow from source to drain. However, we cannot. Why? Because this one has lower voltage. This one has lower voltage. Then then you can think this is just a switch. But how then we can make the current flows from source to drain is we add voltage at gate here. So maybe the 5 volt, for example. Then what happens? Here this is a metal, and then there is a high voltage there. Then what? Electrons are gathered here. And then what? And then the particles are remained this side. So then what happens is that here I just said there is a capacitor, and then this capacitor starts to have energy, right? Because capacitor, once we have some voltage there, then what? In between the capacitors, the energies are gathered here. So then what? Once this capacitor is fully charged, then what? Still current cannot flow. Why? Because this is still insulator. However, electronic field influences this side. So then what happens is that these positive particles attract electrons here. And then it starts to create channel here. This is a channel in transistor. And then using this channel, current flows from source to drain. And then I just mentioned that when we talk about the size of the transistor here, then initially this size indicate channel length, right? So then we can guess that this channel length is smaller than what? It actually indicates better quality transistor. Why? Because if this length is smaller, then it's easier to make channels. We need less energy first. And then also it takes less time to make these channels. So these transistors keep switching. How many times? Maybe 2 billion times per second. So then making this channel takes longer time than we can switch these transistors less times per second. So that this channel actually determines frequency of the CPU, and also it determines energy consumption. Okay, because if this is smaller than we consume less energy. So that's why making the channel size smaller is important. So the slide shows that here gate has zero, then the zero voltage, then no current can flow. So the behaves like insulator. So transistor becomes insulator. But once the gate has some voltage here, then their channel is established, and current can flow. That's how transistor operates. The gate has zero, then so this is the PMOS. PMOS is the opposite of the NMOS. So you can see this is a PPN. But still, it's almost same. But the difference is that here gate has 0 volt, then they have channels here and current flows. Here, this N type has a high voltage, by the way, all the time. And then also gate has 1, then it becomes insulator. Again, it behaves like a switch, but we just need to handle this PMOS, the opposite of NMOS. So again, this is NMOS and this is PMOS, and then gate is 0, then NMOS becomes insulator and PMOS becomes a conductor, and the gate is 1, then NMOS becomes conductor, and PMOS becomes insulator. So do you have any questions so far? That's how transistor operates. And then why is this important? Is because you need to understand that when we use the CPU, then what we need to build these channels, and then what we are building, making this, creating this channel takes time, and also consumes energy. If it consumes the energy, then also what happens? Energy doesn't disappear, right? Electricity energy converted to some other energy type, right? What does it become? Yes?
Heat.
Exactly, right? So what if we consume more energy than what? It actually produces more heat. So this heat actually limits our processor size. So we want to add more transistors there than what? Then which means that what? We have more channels there, and then also every second we switching more transistors per second. Meaning that what? We consume more energy. Then we need better cooling technology. But actually that's also quite hard nowadays. So nowadays people use some water cooling and also some the other types of cooling method, but we are actually almost also almost I don't want to say maybe the end, but it becomes harder and harder now. But once so I just said that even the cooling technology almost hit the technology end. However, once we can make this transistor size smaller, then all problem is solved, right? Why? Because we need less energy to create these channels. Then what? We can add more transistors because each transistor produces less heat. And also, we can increase frequency. Why? Because creating the channel becomes faster. That's why making transistors smaller is really important. That's so currently TSMC does the best job. So I think maybe the time is up, and I will discuss this